So next thing we'll talk about is this idea called coefficient of variation. So let's motivate this with an example. Let's say that we have two sets of numbers, and one set of numbers happens to represent heights of women, and one set of numbers represents weights of men. And typically you would be given the summary statistics, i.e. the mean and the standard deviation from each group of numbers. Because in practice, these are easy to find for these data sets because you would just enter in each set of numbers, all the heights of women that you collected into your calculator, and your calculator will give you the mean and the sample standard deviation. But since we're just now starting to talk about standard deviation, let's practice coming up with reasonable numbers for the standard deviation. So let's start with heights of women. So usually it's easier to think of what it means to do the mean. So what do you think the mean or the average height for women are? Let's say in the US.
Like 5'3", I think.
5'3"? What do you guys think?
I was thinking like 5'6".
Yeah, maybe a little bit more. Maybe in the US, maybe it's like 5'5", 5'6", right? So let's say 5'6". So now let's think about what it means to be a standard deviation. So we said that this variable heights for women is distributed in what kind of distribution?
Bell curve.
Yeah, bell curve. So we know that we have this bell curve that represents heights of women. And we're saying that approximately the mean, where the most number of women having this height would be 5'6". Okay, so being a bell curve, we said that there was this definitive relationship where 95% of all values end up being within 2 standard deviations of the mean. So it turns out that in statistics, that 95% we say are values that are considered typical. So when we say typical in statistics, we actually mean within 95% of the mean. So again, this weight example we talked about, for example, 95% would represent values within 2 standard deviations of the mean. So in that example, what are all values for weights within 2 standard deviations of the mean?
140 to 220.
Yeah, this 140 to 220 here. So because that represents values within 95% of the mean, we say that those represent typical weights for men. So typical weights for men would be everywhere between 140 to 220. And everything outside that range would be considered not typical, would be unusual. So the usual or typical values would be within 2 standard deviations of the mean. So back to this case, if we're saying that heights of women are typical within 2 standard deviations, then let's first identify what heights we consider typical. So, for example, what is the height of the tallest woman that you would still consider to be normal or typical? So there's some woman out there who's 7 feet tall, for example, but that's not considered typical. Or if you saw a woman who's 7 feet tall, you would think that that's kind of unusual. So what height for women would you say is tall but still considered usual? 6 foot? So if you saw a woman who's 6 foot tall, would you say that she's unusually tall or still in the usual range?
Right on the.
That's tall.
Maybe right on the edge. Okay, okay. So what we're doing now is very subjective. So don't worry in terms of being tested on this. The point is that we're trying to together come up with a reasonable number for standard deviation. So this is just practice. So remember, this being a bell curves are symmetric. So if we go the same distance from the mean in the other direction, then that would represent the shortest typical woman. And what would that be according to our numbers here?
5 foot.
Yeah, so because we went 6 inches from the mean to the tallest typical woman, we're gonna go 6 inches in the other direction, and that'll be 5'6" minus 6 inches, which would be 5 foot tall. So do you think these numbers make sense? Shortest typical woman is 5 foot, tallest typical woman is 6 foot, and the average is 5'6". So if these numbers are actually true according to our data, then yeah, we can use them. So let's say that they are. I would say that the shortest is probably a little bit shorter than 5 foot, tallest is maybe a little bit shorter than 6 foot, mean is maybe a little bit less, but let's say that this was correct. The point is, it's just trying to identify a reasonable standard deviation. So these values here at the edges represent the typical values, and they constitute 95% of all the values, or for a bell curve, within 2 standard deviations of the mean. So that means that if we start at the mean of 5'6" and go to the tallest typical value, 6 foot tall, that is supposed to represent adding 2 standard deviations to the mean. And in adding those 2 standard deviations to the mean, we're actually adding how many inches? 6 inches. So if 6 inches constitute 2 standard deviations, then 1 standard deviation should be how many inches?
3.
3 inches, very good. So that means that 1 standard deviation would be 3 inches according to this estimation. So, of course, we don't know what the actual value of the standard deviation is unless we have all the data in front of us. But this is a very good estimation. If somebody so we should expect somewhere around 3 inches for the standard deviation. If somebody said that maybe it's 6 or 7, then you know that that's can't be right, because it needs to be approximately 3. Okay, what about for weights of men? Let's do the same thing. So we know that it's distributed as a bell curve. We kind of did it over there, but let's assume that my numbers are not right. What do you think a reasonable average weight for men would be?
170?
So let's say 170. And we're gonna ask the same question as if you go to the extreme weights that still represent the typical weights for men, what would be the heaviest weight that is still considered usual?
200?
200. And if we did that, remember this being a bell curve is symmetric, so we went how many pounds from the mean?
30?
Yeah, 30, so we have to go 30 in the opposite direction, so that would be 140. So does this make sense as the lightest weight for men? So the lightest weight that's still considered usual for men.
Yeah.
So let's say it is, and if we consider 200 as being the correct number, then now we ask, what is the value of 1 standard deviation? Because going from the mean to the most typical weight constitutes 2 standard deviations. So therefore, 1 standard deviation would be what?
15?
Yeah. So this is the mean plus 2 standard deviations. So therefore, 1 standard deviation is going to be half of this 30, which is 15. So 1 standard deviation, therefore, is going to be 15 pounds. And the mean is going to be what we estimate to be 170.
So you're saying every single time the typical one is 2 standard deviations?
Yes, so for any bell curve situation.
Gotcha.
Here, we happen to be measuring heights and weights, which we know to both be variables that are distributed as bell curves. So anytime you have a bell curve, the extreme variables are plus or minus 2 standard deviations from the mean. And we take half of that to get the actual standard deviation. Any questions? Okay, so the point is that now we have the standard deviations. Typically, you would just be given these 4 numbers, but we just did some practice just so that you can get a feel for how to estimate a reasonable standard deviation. So let's say that you were given these numbers. And you were asked, of these 2 data sets, which data set has more variation in its data? And so in its numbers, which data set has more variation? Heights of women or weights of men?
There are 2 completely different types of measurements, so I feel like that'd be kind of difficult to say.
Okay, so without even looking at the numbers right now, if you were to ask which group of numbers has more variation, which remember we said variation was how much spread there are in the numbers. So which data set has more spread in its numbers, or more fluctuation, or more variety in the numbers?
Probably the weights.
Yeah, weights. So why do you think weights versus the heights?
Cause you have like people that are on like, for example, like my 600-pound height, where like, they're like triple the mean, where on the other way, you don't ever find someone who's like triple the mean for heights of women.
Yeah, very good. So just by the nature of weights versus heights, weights is something that is more easily controllable than height, so you would expect more fluctuation in those numbers. So more variation or more spread in those numbers. So we would expect the weights of men to have more variation than heights of women. But now the question is, how do you quantify that? So remember, we've been saying that this standard deviation was a way that we were supposed to be able to quantify variation. So the question is, can you just look at these 2 numbers and say that because the weights of men has a higher standard deviation, that has more variation? Can you quantify it based on this standard deviation number for both groups? So a few of you are shaking your heads no, so why not? So we reached the correct conclusion that weights of men should have higher variation, but the question now is, how do you quantify that? Can you just look at the two standard deviations and compare them and say that because weights of men has a bigger number for the standard deviation, therefore weights of men should have more variation? So it turns out in this case, coincidentally, weights of men seems to have higher standard deviation. But can we just use that number to always conclude which set of numbers has higher variation just on the standard deviation number? Yeah.
Not for every scenario, because it depends on what you're measuring.
Okay, very good. And the point that you made before is that both these standard deviations has a different unit associated with it. So this standard deviation is pounds, and this standard deviation is inches. So you can't just compare them because that would be comparing like apples to oranges. So let's talk about now how we quantify which group of numbers has higher variation. And so we said we can't just compare these 2 standard deviations, so we're gonna have to normalize them somehow and have them be the same number, the same units before we even try to compare them. So the way that we normalize them first is this concept called the coefficient of variation. So the coefficient of variation is we're going to take each standard deviation, the first one is going to be inches, and then we're going to divide by its respective mean. And then we'll do the same thing for the weights of men. So here, if we take 3 inches and divide by 5'6", we're gonna have to convert that to all inches to be consistent. So what's 5'6" inches in inches? How many inches is it?
Yeah,
66.
Okay, very good. So 12 inches in 1 foot. So 5 foot is gonna be 5 times 12 inches, which is 60 inches. So 60 inches plus the 6 inches is 66 inches. So if you take 3 divided by 66, what fraction or what decimal do you get?
0.045 repeating.
Okay, so 0.045 repeating. So this is a very small decimal number, and sometimes it's easier to think of decimal numbers as percentages. So what would this be as a percentage?
4%?
Yeah, about 4.5%. Okay, so for the heights of women, this has a coefficient of variation of 4.5%. Let's do the same thing for weights of men. So we're gonna take,
0.08.
yeah, very good. You're gonna take the standard deviation, divide by the mean, so 15, divide by 170. And what was that again?
0.088.
0.88. So as a percentage, that's gonna be 8.8%. And now we can compare the variations directly after we normalize them and convert them to coefficient variations. So now we can compare 8.8% to 4.5%, and because 8% is more than 4.5%, we can say that indeed weights of men has higher variation. Any questions? Alright. So here we saw that the rationale for using coefficient of variation was to compare the variation between 2 groups of numbers. And we couldn't directly compare the standard deviations because the units were entirely different. So we had to normalize them first and use this coefficient of variation. But let's say that we had an example where the units were basically the same. So let's say that you're trying to compare the variation between heights of trees versus lengths of bugs, let's say. And let's say that you have the mean and standard deviation of each. So let's say the average tree, let's say, is 10 feet tall. And let's say the standard deviation it's 1 foot. Versus, let's say the average length of bugs, the mean is, let's say 1 inch. And let's say the standard deviation is 0.2 inches. So the point is that if you compare the standard deviations here, initially the units look different. They're foot and inches, but they're both units of length. So you can easily convert both of these into inches. So the standard deviation for heights of trees, instead of 1 foot, would be 12 inches. Or 12 inches. So the question is, because both these units are now in inches for the standard deviation, can you just compare these two and say that the heights of trees has a higher standard deviation, and therefore there's more variation in the heights of trees? Do you think you can conclude that? Yeah.
No, you couldn't conclude that, because it's still, like, we haven't considered the gap between the standard deviation and the mean.
Yeah, excellent. So the standard deviation, recall, is an estimation of the average distance that each tree is away from the average height of a tree. And likewise, the standard deviation of a length of bug is the average distance that each bug is away from the average bug. So just because the average tree has a distance of 12 inches away from its mean, doesn't necessarily mean that there's a lot of variation. You have to look at what the average height of a tree is. So if the average tree is 10 feet tall and the average distance is only 1 foot, then that doesn't necessarily is a large distance compared to the average. So the point is, to find which group of numbers has more variation, you need to compare the standard deviation to the mean of the group. And that's exactly what the coefficient of variation is doing. So even if the units on the standard deviation are the same, you still want to use the coefficient of variation. So let's convert each of these to the coefficient of variation by taking the standard deviation and dividing by the mean. So in this case, we're taking 1 foot divided by 10 feet, or 12 inches divided by 120 inches, and then we're gonna get, what?
10%.
Yeah, 10%. And let's do the same thing for the coefficient of variation for the lengths of bugs. So that'll be 0.2 inches divided by 1. So this ends up being 20%. So now we compare the coefficient of variations directly, and 20% is higher than 10%, so therefore lengths of bugs will have more variation than heights of trees. Any questions? So the point is that anytime you have two groups of numbers and you want to know which group has higher variation, more spread in its numbers in that group, then you would compare the two coefficient of variations of each group together. So you would compare the coefficient of variation of group 1 to the coefficient of variation in group 2. And the coefficient of variation is nothing more than the standard deviation divided by the mean. So coefficient of standard deviation 1 divided by mean 1 compared to standard deviation 2 divided by mean 2. So this is what you're supposed to do. Compare this quantity in group 1 to this quantity in group 2. The point though is that sometimes in real life, people can get away with comparing just the standard deviations together and ignoring the means, but you can only do this in a very specific instance, and when is that? When can you ignore the means? When you're trying to decide which group has more variation. Yeah, if they're both 1, you can do that. What other situation can you do that?
If it's a bell curve?
Not quite. So you're supposed to compare these ratios. But sometimes you can ignore the means and just compare the standard deviations.
If the units and numbers are the same for the standard deviation or similar?
Yeah, very good. So if the two means are actually the same, then you can ignore the means, because if you were to convert them to their ratios, then they offset each other anyway. So if the means are the same, then you can just compare the standard deviation. But that's only under a very specific circumstance. So for example, if we had test scores between 2 different states, for example, and we want to know which state has more variation in its test scores, then you're supposed to compare these 2 ratios together. But you might see that maybe they'll end up just comparing the standard deviations. But they only are able to do that if the means of the test scores are the same for both states. Then you can just compare the standard deviations. Any questions?